In both the Bohr and quantum models of the atom, there are mathematical functions that describe the motion of the electrons, and for each function there is a corresponding energy. These can be plotted on an energy axis. In the Bohr model of the atom, the energy levels are labeled 1, 2, 3, and so on. These represent different two-dimensional orbits that an electron would take in moving around the nucleus. Note that this picture is not to scale. The energy gap between n equal 1 and n equal 2 should be much larger than that between 2 and 3. In chemical species that have only one electron, the energy levels in the quantum model are the same as in the Bohr model. In the diagram, each individual line represents the energy of a three-dimensional orbital that the electron, modeled as a wave, moves in. The difference is that in the n equal 2 level, the quantum model predicts 4 modes of motion, or orbitals, which we label 2s and 2p, whereas the Bohr model has only one. In the n equal 3 level, the quantum model predicts 9 different modes of motion, or orbitals, which we label 3s, 3p, and 3d. If we have only one electron, the energies are the same. Both models are able to predict the emission spectrum of the hydrogen atom. In fact, if the quantum model did not predict the spectrum of the hydrogen atom, it would have been rejected long ago. The power of the quantum model is evident in chemical species with more than one electron. There are many more lines in the emission spectrum than the Bohr model can account for. The conclusion is that there must be more energy levels available to the electron than is predicted in the Bohr model. In the quantum model with more than one electron, the 2s and 2p orbitals are at different energies. Likewise, for the orbitals with n equal 3, the 3s, 3p, and 3d orbitals are at different energies. Now, why would that be? Remember that we are talking about electrons that are interacting not only with the positively charged nucleus, but also with the other negatively charged electrons. We should not be surprised that an electron in a spherical 2s orbital would interact differently with the spherical 1s electrons compared to an electron in a 2p orbital that resides along one of the 3 axes. Thus, we should not be surprised that a 2p electron should be at a different energy than a 2s electron if there are 1s electrons present. Finally, a word about terminology. In both models, we talk about levels. For example, the n equal 1 level. But in the quantum model with more than one electron, levels can split into sublevels. The n equal 2 level splits into the 2s and 2p sublevels. Likewise, the n equal 3 level splits into 3 sublevels. You may have learned the term shells and subshells. Chemists use the language of levels and shells interchangeably, so either is okay. Although when looking at an energy level diagram, we tend to speak of levels and sublevels more often.